You'll ever stop writing P when you need to write P or vice versa?
Yes, all the time.
Okay. I just mean.
Yeah, no, you're not alone.
Where did that done?
Where did you come to the first time bar?
I went to the depths of hell and I thought the state.
I think
They give me one and that's it.
I can't figure it out.
Number one is awful. I got number two, but
Number
I
one
did
is-
not.
What is it?
On the,
Get them banned.
you haven't tried it? I thought I'd gotten it.
I know, I'll be honest with you.
Yeah, they're okay.
I was working
I
on
don't know
it
what it
yesterday,
is.
and I'm like,
Bro.
oh, this is not okay.
It is worth a quarter of an exam. I mean,
You're just trying to like heighten our blood pressure, aren't you?
to heighten your ability to trust me that you kind of only have.
My
to
doctor's gonna be
over the
like,
last,
why is your blood pressure
several months.
so high? Like, that's my ochem.
Is it a stage?
What? Probably.
Oh.
You're
CPUs.
monthly organization. Did you see the professor for
Oh.
it's Diana Forbes, and I couldn't find anything about her. She's probably the fall. And that's it.
Drop on.
She looks younger. She's blonde hair.
Really?
Yeah.
Is she like new?
Yeah, she's new. She literally came through the fall, so there was no ratings on her.
Are
Even
you
at-
talking about a physics group?
Yeah.
She like came into our lecture one day and taught as part of her like interview. Like she seemed fine.
She seems fine.
Well, she talked really, really quickly,
Oh, no.
but I'm sure she would post the notes after.
Yeah. Okay.
She seemed nice though.
That's good. She like looked like she would be good, but I didn't want to like be like anything at the time. But I literally cannot find anything. I just found her LinkedIn. I was like, oh,
Really?
okay. Yeah, she looks younger. And I got into the lab and I got into the CH and yeah, they do. Yeah, good. It's literally one credit and you're good. And then I mean, a couple of numbers, I was like, wow.
You updated the same one?
Wait, are you guys?
Then I have it.
Okay. Did you get the meeting?
See, I think it's quite early. I just pick it up because I should have been there.
Yeah.
Yeah, I did that too, but my alarm.
Oh, no, but we just have
Don't do that. I set it to like, I got a feeling because set it and I like, I'm 20 minutes since it. I felt so bad.
I have to go. I went to the one on Tuesday.
Oh, wait, I tried to.
Oh, no, I woke up this morning.
Well,
And I could see if the banner was done and actually. it
So,
wasn't.
I did research.
Like 2 hours.
But
And
it's
it's
like,
like,
not
my
responding, so I don't know if I'm gonna do that one anymore.
I know like what to do.
I need to actually do stuff instead of just like not doing anything. So they said they're gonna have some fun professors there. Yeah.
I don't know. I don't remember earlier like
You got any plans this weekend? Oh, no, mom's coming up.
Yeah.
All right, good morning.
Are you helping them?
Okay, jumping into reactions. So, some new reactions of benzenes that we have to learn. The first of these is the Burt reduction, which is actually really useful because it's a very good way of making isolated dienes. And isolated dienes are hard to make because if you try to do a normal E2 type elimination, you're going to favor your conjugated diene, right? Because that's a much more stable system. So this guy, he's an Australian chemist actually, which is kind of odd because there's not a lot of Australian famous chemists, but figured out, and I'm sure what happened is he was trying to do kind of an alkyne reaction, the metal ammonia with alkyne, and had a benzene in there and found that the benzene got reduced too if you pushed it too far, and then basically developed this as a way of making these isolated dyes. Okay. The mechanism is pretty close to the metal ammonia reduction in that the reactivity that drives the metal ammonia reduction of an alkyne is the same reactivity that drives the reduction of benzene. Okay. So, mechanism, what's to be the first step then? We're going that. So our most reactive species is sodium, right? And so that wants to, why is it reactive? It wants to give away its electrons. So it's going to give it to one of the carbons on benzene. Benzene's all the same here, so it doesn't really matter where we give it. That gives that carbon too many electrons. And so we have to break that pi bond, separating and not sharing those electrons anymore, giving them each of the positions. Okay, so when we do that, that stays the same. This now is the anion, and then this is the ring. With me so far. Looks very similar, right? And then there are a bajillion resonances here, okay? Because you can do resonance with the radical, and you can do resonance with the negative charge. All right. Depending on what book you look at, they'll focus on one or the other of these. I'm going to try to make our lives easy and just do one set of resonance structures that we're going to look at, which represent most of the stabilization that we have. And it's also going to help us when we need to predict where our groups are going to go. Okay, so if you see this done differently, it's not that it's wrong, it's that we're choosing to focus on one set versus another. Make sense? Okay. So what I want us to do is to not mess with the anion and stabilizing that, which we could, right? We could start pushing that around, but instead look at the effect of moving around and stabilizing. Does that make sense to everyone? Okay. So in order to draw resonance, one electron, gets us to here. Okay, double bond. Oops. Single electron there. That bond stays there. And then we can do it again. One electron, electron. Okay, there. Okay. So those are the major resonance forms that we're going to do, and we're only going to draw the resonance for moving the radical, not the anion, even though both are possible. Okay. And we'll see why when we get to the next step. All right. This actually explains how we get to the isolated diene as opposed to a conjugate diene. All right. Do you think it's better to have a lone electron and a lone pair next door to one another like this, or further away, or next door? What do we think? Further away, because there's electron repulsion, right? So this right here is our major resonance form, and the one that's going to then lead us to quarks. Does that make sense? So even though we started with this, it's the resonance stabilization that gives us our new reactant. Okay. Once we understand that, we're just going to continue the process. There's usually, I would say sometimes, not always, there's some proton source in here, like methanol. You can get away with the NH3 as a proton source, but it's not great. It's much better if you put a more acidic hydrogen in there to facilitate this reaction. Okay, so that's what we're going to do. Use that methanol as a proton source. So now what we're going to do is go ahead and react with the anion, or proton transfer, and get us to there, right? Because there was already hydrogen on the benzene. And there are resonance structures here. We're not going to mess with them. We're going to leave this where it is. And go ahead and take a second equivalent of the sodium, pair up that electron. So it's a half-headed arrow here when we talk about the motion of one electron. So half-headed arrows in all of these. Gets us to the electron pair. And then we just repeat our proton transfer acid-base reaction again to get to our final product. So it's addition of an electron, Resonance, proton transfer, addition of electron, proton transfer. Okay, any questions on that? All right, that's with benzene, no groups on it. The moment we start putting groups on benzene, things get a little more complicated. All right, so we have to think about what's going to happen and why as we go forward. We can actually simplify things for ourselves by explaining why this is the rule, but by kind of remembering the rule about what the type of group we're putting on the ring is going to influence where that group ends up in the molecule in the 1,4 diene. Okay, that makes sense to you? So electron withdrawing groups, remember electron withdrawing groups have the partial or full positive, one electron density. These are things like your CN, your nitrile, your nitro, SO3H, C double on ketones, esters, amides, etc. As long as it's a carbonyl that's directly attached, that's electron withdrawing group, etc. When we have those groups on there, so that would be something like this, your substituent is going to end up on the sp3 carbon. Okay, so you draw your 1,4 diene, and that substituent then has to end up either here or here, not on any of the sp3. Does that make sense to you? We have an electron donating group, like anything with a lone pair on the atom that's directly attached, so oxygens, nitrogens, sulfurs, alkyl groups, those don't have a long electron pair. We talked about how those are mildly electron donating, which we know from carbon stability. These are going to end up on the sp2 carbon. All right, so these are our sp2 carbons. We have one group on there. All right, let's see this reason. Okay, makes sense? All right, so why? Why do we have this? All right, we think about our mechanism again. So we can take and donate our electron into our ring system. Now, this in and of itself gets more complicated because in benzene itself, all three of those double bonds are equivalent, right? Here, if we react here versus here versus here, we get different answers. Right? So what I want you to do is you focus on reacting at the double bond that's attached to the group, whatever it is. So double bond attached to the group. Does that make sense? So when we do that, I want to split that double bond apart, and I want to either do this. Put the electron pair here, or the radical here, or vice versa. Okay, so let's think about this. Let's do it the first way. So if I do that, if I get to that. Okay. If this is an electron donating group, how good is it to put this full negative charge next to an electron donating group? Is that good? No, because electron donating has excess electron density, and we just put the most electron-rich site directly next to it. If instead of doing it that way, we did it the other way and switched it around, that's going to be much more stable. Okay, so our choices are either doing this or that. And this is far superior in terms of stability because of the electron donating ability. That's a more stable intermediate. Okay, does that make sense to everyone? Okay, so we don't want this, we do want this. Okay? And with this, look at both options here. We're either going to get one pair there, or the lone pair there. In this particular case, which is better? Putting the negative charge next door to that partial or full positive, or putting it further away? Closer, right? Because the opposite charge are going to stabilize one another. Okay, so in this case, this is the arrangement that we want, not that. Does that make sense? Okay. If we then go and draw our resonance structures, and once again, we're going to move the lone electron, not going to move the whole pair here. Now we have this. Double bond here, double bond here. Okay, and starts there. And then if we do it again, get two there. There. Okay, so those are our resonance forms that we get from that structure. Make sense to everyone? Let's see how I got there. Okay, I didn't move the negative charge. Any of them? Oops, I didn't. Okay, the charge is here still. And I only did the resonance with the radical. That got me there. Do it again. Got me there. Make sense to everyone? This 1,4 resonance form is the one that leads to the product. So when we protonate and then pair up and protonate again, our product okay, so what we see here is our electron donating group ended up on our sp2 hybridized carbon, which is what we said was going to happen. Does that make sense to everyone? And then similarly, when we draw the resonance using only the radical here, we're going to basically make the system where the double bond, our radical, like that. It's here, that double bond stays put. And now our other double bond is here, and our radical is here. So, and then we do it again. Now we're going to go, let's see which direction we're going up. Here. Still our negative charge there. This time our lone electron is here, our double bond is here, our double bond is here. Okay. The only one we care about in terms of our resonance forms is this one right here, where they're in the 1,4 arrangement away from one another. So we protonate, partner the electron, protonate again, and then what we can see is our double bonds stay here. So these are our sp3 carbons. Our electron withdrawing group ends up on the sp3 carbon. Does that make sense? So this and this too. And so it doesn't matter what this group was, what type of electron withdrawing group is. Withdrawing group it is CN, NO2, SO3. We don't care. As long as it has that partial or full positive character, it's going to want to be closer to that negative charge, which is then going to lead us to these resonance structures. Right? The other one, no good. Doesn't get us. Does that make sense? That's how that all works. I do have an example of multiple. All right, let's say we have this. And we do NaH3H. Okay, we know we're going to end up with isolated diene, And we know this has to stay in a 1-3 relationship because our groups and our mechanism never move their position on the ring, right? We're not going to disconnect carbon bonds. Right. But they can be in a 1-3 relationship here and here, here and here, here and here, etc. Okay. Actually, this is not going to work out because we can't get the 1-3 in the right position. So let's do, sorry, let's make this a carbon. Yeah, we'll make it this. Sorry about that. Maybe we can work out. Okay, so we got our 1-3 relationship. This is what type of group? The ethyl. Electron donator and electron withdrawing. Donating, so it has to be on what type of carbon? sp2. This is EWG or EDG? EWG, so it has to be on a sp3. So I need to start with my ethyl group either here or here. Okay, or here, it doesn't matter which one. And then in a 1-3 relationship, I need to have my other group on an sp3. So if I put that here, I can't do a 1-3 relationship over to here because then I get them both on sp2s. But if I start here and put my other group here, that's still a 1-3. That's going to put the electron withdrawing group on the sp3 carbon. Does that make sense to everyone? Okay, so that would work. There's my ethyl. There's my ester. That would be a correct product for the Birch reduction of the system. Okay, does that make sense? So I guess I could have done another one. I would have had to do here and here, and I could have done the first one. But trying to think and teach at the same time, not always conducive to being successful. Okay, make sense to everyone? So that's the game we play. That's Birch. Any questions? If you were to do the mechanism for this, you just have to either pick this double bond or this double bond to start with. Okay, and then you're going to go through the process. If you start with this double bond, you want your negative charge not here but here. Okay, and if you start with this double bond, you want your negative charge here. And then draw your resonance structures with the radical, not with the anion. As I said, if you look at online and different online tutors or things, they'll either do it this way or they'll do it the opposite way where they move the negative charge, but it's still the same answer because you still don't want the negative charge next to the electron donating group, or you do want it next door to the electron withdrawing. But you have to pick which one you're going to do. Okay. Does that make sense? All right. Okay, no questions on that. We're going to move on then to Buckle's rule and aromaticity. So what we're going to try to do here is we're going to try to put molecules in boxes. And we're either going to say a molecule is in this box we're going to call aromatic, box we call anti-aromatic, or it's neither of these two things. So these two things are special. And aromatic means it has special stability. Anti-aromatic means it has a especially unstable arrangement of its electrons. And then non-aromatic is the last one. It just means it's something, it's just a normal molecule. Okay, it could be any of these that we grew, whatever. It's just not anything special. It's a non-aromatic. So what we need to do is we need to have a way of looking at a molecule and analyzing and see if it has one of these two special arrangements, special boxes to go in, or is it just normal and we're not going to worry about it? Okay. We already know about benzene. Okay. Benzene is an aromatic compound. It's called an arene because of the aromatic character. And it has special stability. When we did our reactions, we never messed with the benzene, right? We left it alone and said it was just going to kind of hang out there and not do anything funky. It's because it's especially stable. Okay. And there are other molecules besides benzenes that have the same stability. So we're going to learn why and how to tell when that's the case. Okay. Conversely, this anti-aromatic, it's not just a reactive molecule, but it's a super duper unstable molecule, like benzene is a super duper stable molecule. Okay, so you can take this and do HX, and we know that double bond's going to react, right, to give us that. We do benzene, which is an aromatic compound, we do HX, and we still have benzene, right? It doesn't do anything. And HX is a superreactive system, so we know that this is especially stable. Okay, so we want to figure out other molecules that are like benzene. And then anti-aromatic is, and the analogy I used to use, and I'm still going to try to use it, but it's probably not going to work, is from Seinfeld, and or if you want to back up even further, the Superman comics. There's Superman and there's Bizarro Superman. Okay, Bizarro Superman is the exact opposite of Superman. Superman stands for good and wants to help people, despite what they did in the new movies where they kind of made him a little complex. But he was like, you know, the symbol of peace, justice, super strength, everything. Bizarro Superman was just as strong, but he was evil and the exact opposite. Okay, so still super strong, but super strong in a bad way versus in a good way. Seinfeld. I know you're familiar with Seinfeld, but nobody's seen every episode like we used to. We did it on Thursday. Did it with the characters of Seinfeld. So Jerry, Elaine, George, and Kramer. They had their bizarro versions. And so Kramer is kind of a klutz and a goof, and he was all put together, and he was, you know, always dressed in a suit and stuff like that. And, you know, George, and so he was all put together. So they were all opposite of one another. That's what this is. Okay. So we're trying to figure that out. This guy, a long time ago, was able to predict the behavior looking at molecular orbital diagrams of the pi systems of rings. Okay? And so he was able to kind of do this analysis and then come up with sets of rules as to what would make something potentially aromatic or anti-aromatic. All right, so you all with me so far? That makes sense? Okay, so we got to do walk down memory lane here. You probably saw something like this in general chemistry, where you were looking at energy level diagrams. We did a little bit of this with our hybridization stuff. Okay, you can do this with your pi orbitals, p orbitals, well, pi systems, and look at energy. So if we have, let's just say this. We can draw an energy level diagram for our systems. And so what we do is we have 4 p orbitals, right, that form pi bonds, and then they become pi bonds. So you have atomic orbitals with p orbitals, your molecular orbitals are the pi orbitals. And by the orbital conservation rule, the number of atomic orbitals is equal to the number of molecular orbitals. So this is 4 molecular orbitals. We have 1 electron in each of those 4 orbitals, and we fill from low energy to high energy, following Hund's rule, Pauli principle, Aufbau principle, just like we did with our electron configurations. Okay? So if we have 4 pi electrons here, 4 pi electrons, 1, 2, because we put 1 in each equal energy orbital, so they're all half full, and then we fill them up. Opposite spins, since there's only 1 at this energy level, we go 2 and 2. Okay. When your orbitals are full, okay, like this, these are called bonding orbitals because they're completely full. Okay. If we had just 1 electron in there, we call that a non-bonding orbital. If you don't have that, that's what that's called. And when they're empty, these are anti-bonding. So you can do these for these pi systems. You can draw these orbital diagrams. Okay. In order to do it for cyclic systems, we use something called a cross circle. Okay. And the way you do this is you draw a circle, and then we'll inscribe whatever polygon is associated with the shape of the molecule that we have. Okay, so for example, if we'll do cyclobutane, and we'll do benzene. Okay. We'll talk about why these are high bond risks. All right. Well, what you do is you inscribe the polygon into the circle, and there's one important caveat. Okay. So inscribe polygon into circle, and it's starting with a corner at the bottom. And we must start with the corner at the bottom for this to work. And then wherever a corner touches the circle is where an energy level / orbital is. Okay. So if we try to do this with our cyclobutadiene here, we're going to start always at the bottom. And now we're going to draw a square into that circle. And then wherever a corner of our thing touched the circle, we have an energy level or an orbital. So we're drawing the energy level diagram for this thing. We're doing that. Okay. I just reduced down the bottom, two at the same place, higher in energy, one higher in energy than that. Okay, you with me? Okay, if we do this for benzene, here's our circle of benzene, there's our lowest point. We're going to start with the corner there. And there's our hexagon inscribed inside that circle. So an energy level here, 2 equal energies there, 2 equal energies there, and we're at the top of the circle. And so now this energy diagram would look like that. All right, you with me? All right. Then what we do is we count up the number of pi electrons, because what we're doing is drawing the pi molecular orbital energy diagram. Okay, so how many pi electrons do we have in that structure here for cyclobutadiene? How many? 4, right? 2 here, one electron overlapping from a pi bond, one electron overlapping from a pi. Okay, there are 4 pi electrons here. For benzene, how many do we have? 6. Okay, and there's 6 pi electrons on benzene. Okay, so if I want to then draw the energy level diagram for this molecule, I need to then fill this orbital diagram with 4 electrons. So 1, 2, pair it up. 3, 4, because I'm going to put 1 in each of the equal energy orbitals, so they're all half full. With benzene, 1, 2, 3, 4, 5, 6. In terms of bonding and non-bonding, this is bonding, this is anti-bonding. And this, what did I say was? Non-bonding. Okay. Over here, all of these are in bonding orbitals, and these are all anti-bonding orbitals. Okay. When we get these 2 electrons unpaired in these non-bonding orbitals, this is essentially like having a diradical, right? Because it's an unpaired electron and an unpaired electron at 2 different locations. What do we think about the reactivity if we just had 1 unbonded electron? What do we know about radical reactivity? Pretty reactive, right? Things 2 in the same molecule, what do you think? We created bizarro supergroup, right? We made it especially unstable by having these electrons unpaired in these unbonded ones. And so what this guy Huckel realized is he could predict whether these molecules would be especially stable or unstable by looking at these energy level diagrams. Okay. With me? Okay. Anytime we had this type of arrangement, he basically said it couldn't exist, which was kind of wrong. This can exist, but you have to do it at like negative 290 or something to stabilize it enough. And even then, it shifts its shape, and it basically elongates your single bonds and shortens your double bonds, so it's more of a rectangle than a square, which then screws with this shape a little bit to make it exist. Okay. But in general, anti-aromatic are not going to form because, and those are going to be anti-aromatic, and we'll have a set of rules here for in a second. Whereas when we get these all like this is especially stable, and we don't want to disrupt this. Okay. So far, so good. So that's the history behind where we get to. And basically, he then was able to summarize what was necessary to get to that type of energetic state. Okay? And so there's several things we're going to look at. First thing is the molecule must be cyclic. So this is like the Buckle rule. Basically says you must have a cyclic planar, which just means flat. A cyclic planar polygon of n sides, 3-member, 4-member, 5-member, 6-member polygon, whatever. With, before I get to that, my eraser. All right. Yeah. Of n sides, completely conjugate. Okay. We'll talk about what that means when we simplify, but essentially it means that you have to have the ability to delocalize the electron density throughout the network. Okay. Completely conjugated. If 4n plus 2 pi electrons, and this confuses students, and I'll try to explain it in a second, but if you have 4n plus 2 pi electrons, then you have an aromatic system. So you have to have this, and that true in order to even start considering these two boxes. Okay? If any of these three things are false, you're automatically here. Okay? So if I have this, is that going to be aromatic or anti-aromatic? No, because it's not cyclic. Okay, so it's in this box automatically. We're not going to have a special stability or instability, super special stability or instability associated with it, because it fails on that first. Okay. All right. So if 4n plus 2 pi electrons and all three of these other things are true, it's going to be aromatic. And if 4n, then it is anti. I'm going to try to explain this, but like I said, students always get confused by this for some reason. All right. What does it mean to have 4n plus 2 pi electrons? What's n? Okay. This means that n is going to be either 0, 1, 2, 3, 4, dot, dot, dot. They have to be whole numbers for the value of n. Okay. So basically what we're doing is we're solving for n and seeing if it is one of these things, if it's a whole number or if it's a fraction. If it's a whole number, then this is true, and that's the number of electrons we have, right? 4 plus 2. If it's not a whole number, it's not that, right? Okay, so let's just do 4 plus 2. So 4 plus 2, if we have 12 electrons, okay, is that 4n plus 2? Well, How would I solve this? My equation is 4n plus 2 equals 12. I'm going to subtract 2 from each side, so 4n equals 10. Then I'm going to divide by 4. So n equals 10 fourths, which is 5 halves, which is 2.5. Is that a whole number? So this equation is not true. 12 does not equal 4n plus 2. 12 equals 4n. This number of electrons fits the 4n description where n equals 3. So basically what we're saying here is for 4n plus 2, this is 2, 6, 10, 14, 18, 22, etc. 4n is, can't have 0, 4, 8, 12, 16, etc. These are your 4 multiples that you learned when you were in the 2nd grade, probably, right? 3rd grade, something like that. That's what it is, okay? So you're saying I'm counting up my pi electron. First of all, I'm going to see, make sure, cyclic planar, completely conjugated. If that's true, I then count up the number of pi electrons I have, and I see if it's one of these numbers or one of these numbers. What happens if it's 3? Is 4n plus 2 true? Is 4n true? So what box are we putting in here? None. Make sense? We have 16 electrons, and those other 3 are true. Antimatter falls 4n. Okay? Makes sense? Every year, people are like, I don't get what n is. Count up the numbers, see if n is true in these different equations. All right, so far so good. Cyclic is easy for students to tell. Is it a ring or not? You have your pi electrons. Planar, hard to tell. Okay? How do you know if the ring is going to be flat? In general, if it's fully conjugated, which means you have the p orbital lone pair at every position, we'll get to that. I'm going to say, for the purposes of this class, 8 atoms or less. Because remember back from first semester when we were talking about our non-conjugated system, just our rings, those rings puckered, right? They have fluxional mobility. And the bigger they are, we started introducing more torsional and steric strain, and then they started trying to move out of the way. Okay? As long as you're at 8 atoms or less, you're not so big that keeping it fully flat is doable. But the moment you start getting to 9, 10, 12, 20, you're too big, and those torsional and steric strains start fighting against you, and they start bending. And what that does is it moves the p orbitals out of alignment with one another, so you don't get a good overlap, and that then reduces the stability of the molecule. Does that make sense? Yeah, kind of, sort of. Okay. So for what you need to know for the planar is, are there 8 atoms or less in the ring? If there are, we're going to say yes, that's true, it's planar. If there's not, then we're going to say no, that's not planar, and therefore we're failing in these first 3, and we're automatically going to be non-aromatic. Okay? All right. The last thing, the completely conjugated. What that means essentially is there a p orbital or a lone pair at every carbon of the ring, or every atom of the ring? That's what that means. Okay. You guys with me? Let's do the easy ones with just the carbons first, and then we'll complicate it. That's what we do in this class. Okay. Okay. Alright, cyclic part. You can have spaghetti hanging off of your ring and still have your ring be aromatic, right? We've done reactions of benzene with stuff off of it, right? And we left that benzene alone and we did our reaction over here with our alkyl halide and we didn't need to or whatever we needed to do, right? That benzene was still special, super stable, and we didn't mess with it. Okay, so what we're honing in here is not on the molecule as a whole, but on the ring systems of the molecule to determine if that ring system is aromatic or not. Okay. If the whole molecule has no ring systems, it's not aromatic automatically, right? But we're trying to classify whether this ring here and this ring here is aromatic. Okay. Is this ring aromatic? Is it cyclic? Is it planar? Yeah. Is it fully conjugated? No. These are all sp3 carbons, not conjugated, non-aromatic. It's a non-aromatic ring. It's the same as an ethyl or whatever. Okay. Is this cyclic? Planar? Yeah, 6 atoms. Is it fully conjugated? No. P orbital, P orbital, P orbital, P orbital, but here and here. It's sp3 carbon. So anytime you have an sp3 carbon, you're not fully conjugated in your ring system, right? Because that will not accommodate a p orbital or a lone pair because all of your electrons are tied up in bonds. Make sense? Okay, so no sp3 carbons. The moment you see an sp3 carbon, non-aromatic. Okay? This molecule. What do we think? Okay, is it cyclic? Definitely fully cyclic, right? Question. Is it planar? This ring is 6 atoms. This ring is 5 atoms. Those are both, it's 2 rings there, right? They're both less than 8 or less. So it's cyclic planar. Is it fully conjugated? No, because over here we have an sp3 hybridized carbon. So the molecule itself is not aromatic. There's, not aromatic because it fails at the first 3. However, what's the however? There's a benzene there, right? Is that benzene cyclic, planar, and fully conjugated? How many electrons? 6. 6 is equal to 4n or 4n plus 2? 4n plus 2, so it's aromatic. So we have an aromatic ring in a molecule that is not fully aromatic. Does that make sense? Okay, so the ring here, this is aromatic. This ring here is non-aromatic. And then the molecule as a whole is non-aromatic molecule. So you have to be careful. Are we assessing the entire molecule or are we assessing a behavior of a specific carbon molecule? Okay, does that make sense? Okay. Pretty easy now. What's this one? Non, because we have sp3 carbon, right? In the ring. Cyclic. Cyclic system. Planar. Or p orbital or lone pair at every position. Okay, good. So all 3 of those are satisfied. How many electrons? 2 plus 2 is 4. 4 equals 4n. 4n equals 1, right? So this would be a anti-aromatic ring. And the molecule as a whole isn't a fully aromatic molecule. We don't really care about the molecule as a whole. We're caring about the behavior of individual parts in our molecule in terms of how it's going to behave. Does that make sense? Okay, so this is an anti-aromatic. Okay. This one, hard to see. Okay. Molecule as a whole has the sp3 carbon. It is cyclic and planar because we have 6, 5, and 6. But that right there tells us it's not fully conjugated. We'll see we'll be able to do things like this eventually. We're not get there yet. And that now changes that. Or this now has a lone pair at that carbon, right? So we can do things with that. But for right now, no, but yes and yes, because it's cyclic, planar, fully conjugated, and then 4n plus 2 for each of those. right, make sense? All right, so those are the synthesis steps. Questions on that? Guess what? Is it class over? Please say the class is over. You got 4 minutes. All right. Baseline, make sense? Okay. All right, we can also do ions. And radicals. Okay, so let's do sometimes that lone pair is not going to be drawn in for you, like that, right? You have to know that's there because carbon formal charge calculation, 4 valence electrons minus 2 free bonds shown. There's a hydrogen that's not shown, right? So 4 minus 3, and then in order to get to the -1, you need 2 lone electrons. Okay, so this is going back to the first semester stuff, counting valencies. We'll put it in. Okay. Over here, there's only 6 electrons, which is how we get to our carbocation. Okay. So 1 hydrogen here, 1 hydrogen here, 2 hydrogens here, but I wouldn't draw that in your notes because you want to be able to do it without it, right? And mentally put those in. Make sense? Okay. This one, cyclic, planar. Yeah. P orbital, lone pair. No, right there, no p orbital or lone pair. So this is non-aromatic, right? Cyclic, yep. Planar, yep. Fully conjugated. What is that carbocation? How do we get that carbocation? There's an empty p orbital there, right, that we could use, make a lone pair, and use that to form a bond. Right? So if we did a carbocation reaction of this plus, we're taking and giving those electrons to that carbon. Where are those electrons going? Have to have somewhere, right? And the somewhere is basically an empty p orbital, and this is why this is sp2 hybridized, which means you have an empty p orbital, and then you had your 3 sp2 orbitals with 1 electron in each that are shared. And that's first semester, first couple weeks of first semester that we did, and you didn't enjoy it. Make sense? Okay, so this is a empty p orbital when you have that carbocation. It looks like something stupid. I don't know, you're laughing at something. All right. Okay, so yes, it is fully conjugated system. And we also know this is fully conjugated because you can do that, right? So if you go, you can distribute that plus charge all over around that ring. So it has to be fully conjugated. All right. How many electrons? 2 plus 2 plus 0, right? So 4, so this is anti-aromatic. This one is cyclic, planar, flat, and p orbital. This lone pair is in a p orbital. And we have our sp2s all the way around. All right, and then how many electrons here? 6. So this is aromatic. And how many electrons here? 5. So this is 9. All right. Make sense? All right, so we're going to do heteroatoms, so called heterocycles, where we incorporate a nitrogen, oxygen, sulfur in the ring and see how those are. And then we're done with aromaticity, and we're moving on to electrophilic aromatic substitution. Okay? That's the last chapter of electrophilic aromatic.
I think you raised it.